So we're going to look at nuclear chemistry. This is usually a very fascinating subject because through the years, everyone's heard so many crazy things about nuclear chemistry. They're never really sure what's true and what's not true. Plus, you've got the movies, you've got Marvel, you've got everyone being hit by nuclear things and converting into superheroes. So what is really going on with radioactivity? Is it still dangerous? It can be dangerous still, but there are lots of types of radioactivity that can't even get past your skin. So you want to keep that in mind too. So before we get too far into radioactivity, we need to look at isotopes because we're trying to figure out why does this even happen. So I've got the 3 isotopes of carbon listed right over here. And an isotope is just something that has the same number of protons. And remember, when you have the same number of protons or just the number of protons, that's what tells who you are. So this is 6. And so this has got to be carbon in all those cases. Well, an isotope is something that has a varying number of neutrons. So the proton plus neutron section right here. You can see I've gotten written out here, 12 minus 6 is 6. This has 6 neutrons, this has 7, and this has 8. So the percentage of carbon that you find as carbon-12 is like 99%. And this is very, very stable. It's not radioactive. Then we also have carbon-13, 1% of the time. That's also stable and not radioactive. But then a very, very, very tiny percentage of carbon is radioactive. So it's carbon-14. And what you might be able to assume from this is just thinking, well, if these aren't, but this is, then maybe it has to do with the neutron to proton ratio. And if there's too many, well, then maybe that's what causes radioactivity. Or maybe you'd even think to yourself, what if you had too few neutrons to protons? So let's look at that idea and see whether or not it works. So one other piece of information you want to know going into this is that when we look at a nucleus, it's the nuclear instability that causes radioactivity and decay, things like this. So radioactive decay. What holds the parts of a nucleus together is called the strong nuclear force. It's very short distance. It's only like the length, it's like the diameter of like a proton. So it's not a long distance, but it's super, super strong. And it's what holds everything together. And this is a deal because these protons are very, very close to each other and they're positively charged. And so they just can't handle repulsion issues if they get too close. So we've got the nucleus in between, kind of help to space out our positive charge a little bit. But there is always that tension. So since this is a short force, you could imagine once you get, like 50 of these all together and it's holding them on like an individual basis, eventually you're going to have a situation where there's just kind of some stability issues, and that's what happens. So let's look at a picture that helps us see radioactivity. So notice on the left over there, we have whatever it is, 10, 20, neon. So the 10 means the number of protons. So this is the number of protons, so that's what you get in the corner of the periodic chart. And then this is the number of neutrons. So the reason I have the top number there is because that's 10 protons and 10 neutrons. So this part isn't telling us the atomic mass. Or the mass number. This part is telling us how many neutrons there are. So you can see right here, we're falling at 10 to 10, and we have a nice straight line. The problem is that by the time you get over here, this line is not even part of this. So what are those colored things? Well, the colored things are the non-radioactive but stable atoms. And then there's our radioactive atoms. And our radioactive atoms could exist for like a few seconds. Or it could exist for a lot longer. Like we could be talking about like millions of years. But still, we have a little bit of radioactivity that's released every, so much of a period of time. So they're not really stable. So as we begin to look at this, the blue part, those little tiny blues, those are the only non-radioactive ones. And then the green is the radioactive. You can also see that right here around like just past 80, around like 82. You can see that if you're going up, we kind of just stop having anything that's stable. So there's a point on the periodic chart past him where you just don't get stable isotopes. Everything after that's going to be radioactive in some way. So that definitely implies that too many protons is problematic. And then the green part, you can see we have a wider range of green sitting around all of these right here. So you do also want to know, not for a test, but just so that you know, is that there are a magic number of stability. And we have found that 2 protons, 8 protons, 28, these just are the magic numbers that everything is able to hold together really well. So for example, 10 has has 10 stable nuclei, but the ones on either side, 49 and 51, they only have 2. So that's something else to know, is that we do have these things called magic numbers. So it's so cool. The people who look at radiochemistry, they come up with some really great names for some of these terms. So the other thing I wanted to point out is that as you go along, our line just kind of leaves anything real behind. So the only point at which the whole idea of protons and neutrons being the same is true is when you've got a really small number of protons. What happens is that you do end up being neutron heavy. That's okay in some cases and not as okay in other cases. So what causes a nuclei, or what does it do when it's got too many neutrons? So this is what it does. You'll notice right here, the blue is a neutron, and then the red are protons. And this is the craziest thing, okay? The neutron converts into a proton. Kid you not. It's the craziest thing. So if we were talking about, let's say this is calcium, and it had 20 protons in there, and it had 20 neutrons, it's making a total of 40, then our calcium now has an extra proton, and it's short a neutron. And here's the weirdest part, is that we use this. This is what tells us what the element is. This tells us everything about the element. We look up here. Now we've turned into this. Now this is not really a real decay scheme. I'm just giving an example of like what would happen. When that does that conversion, there's extra energy and parts left over. This part that's left over in that kind of conversion is a beta particle. And it looks like this. It has almost no mass, and it has a -1 charge, which does imply that we have a charged particle over here. This is not the same thing as like ionic bonding or making ions in the way that we've been talking about it before, because we aren't just losing an electron. We actually have a neutron that's turning into a proton that's changing the whole atom into a different atom. And then we also are losing an electron in the process. So know that it is not exactly the same thing, but this is what's going on with radioactivity. There are 3 videos that are linked below if you want to find out and see more about like how the neutron converts into protons, or how the other particles convert into each other just to help with nuclear stability. I'll have them linked below this video.